we're alive.
Right.
So I can't really imagine anything in this book being too difficult since it's all like very foundational. At least it has been. But we're only on chapter 2, so
Yeah.
okay, so it's 2.5
Yeah.
application number systems and circuits. Okay, let's see. So counting in binary is just like counting in decimal if you're all thumbs. The last certain way. In elementary school, you learn the meaning of decimal notation, that to interpret a string of decimal digits is as a number, you mentally multiply each digit by its place value. For instance, 5049 has a 5 in the thousands place, a 0 in the hundreds place, a 4 in the tens place, 9 in the one place. Thus, 5049 equals 5 times 1,000 plus 0 times 100 plus 4 times 10 plus 9 times 1. Using exponential notation, this equation can be written as 5049 equals 5 times 10 to the third plus 0 times 10 to the second plus 4 times 10 to the first plus 9 times 10 to the 0th. More generally, decimal notation is based on the fact that any positive integer can be written uniquely as a sum of products of the form d times 10 to the n, where each n is a non-negative integer and each d is one of the decimal digits 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. The word decimal comes from the Latin root deci, meaning 10. Decimal or base 10 notation expresses a number as a string of digits in which each digit's position indicates the power of 10 by which it is multiplied. The rightmost position is the ones place, or 10 to the 0th place. To the left of that is a tens place. To the left of that is a hundredths place, and so forth, as illustrated below. Okay, binary
Yeah.
representation of numbers. Oh yeah, I mean that's like a super explicit explanation of something we ought to be pretty familiar with.
Yeah. Yeah. Yeah, that was interesting. And yeah, a lot of number theory, like I think like chapter 4 is about number theory. Like a lot of that is kind of about like being explicit about its kind of like arithmetic. Yeah.
Hmm.
Yeah, but that's cool. Yeah, this next part because I guess like that that way of writing numbers is decimal notation based on 10, but that is not the only way we can represent a number.
I guess that's the next logical step here.
Yeah.
I guess I can read this part as well.
Oh,
Binary representation of numbers. There's nothing sacred about the number 10. We use 10 as a base for our usual number systems because we happen to have 10 fingers. In fact, any integer greater than 1 can serve as a base for a number system. In computer science, base 2 notation or binary notation is of special importance because the signals used in modern electronics are always in one of only two states. The Latin root bi means 2. I wonder why you can't have a base 1 number system.
yeah, I guess like the idea of base is like that well I guess if you well one thing is that like whatever your base is, that's how many digits you can use for each place. And like for like in the decimal
Right.
system we have 10 digits 0 through 9, and they can put them in the tens place. Uh but then so we just have base 1, we would just have the digit 1. And then also like the thing is that like so like when you have like a base, like the digits are like places based on the powers of that base. So like we have like in decimal we have the ones place, the tens place, the hundreds place, the thousands place, and then in binary we'll have like the ones place, the twos place, the fours place. But then if we had one, then the powers of one are all one, so we just have like a ones place, a ones place, a ones place, and then in that case, I guess maybe we could just like, I guess if we had a base one system, maybe we could just like, one would be one, two would be one, one, three would be one, 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 maybe something like that. But that wouldn't be as useful because like you'd have to like write as many digits as you have, or
Right.
like the number of digits would just equal whatever the number is.
Right. It wouldn't stack at all.
Yeah.
What is the tally system?
Uh.
You know what I mean?
uh yeah, it would be like a tally system, I guess, if it was base one. Like you kind of just like write however many ones that like equal to the number.
Yeah.
But is a tally system like another system number system?
No, that's exactly what I was talking about. Well, except they use a
Oh, okay.
cross through the four whenever they're representing a five, but otherwise
Oh
it's
yeah.
basically the same thing.
Yeah. Oh yeah. And that's kind of a pun, like basically base one.
Wow.
Yeah.
Hmm. Well, let's see. I mean, I
Yeah.
don't.
And wait, I guess one other thing is that like I guess if we assume that zero is always used, like because zero is always used in these systems, like if you had a base one system and your digit was always zero, then maybe that wouldn't work because then you'd have just every number would be 0, 0, 0, 0, 0.
Right. I mean, I guess it could still have some value. Like you can really see the volume of the number with your animal brain when there's only one digit in the number system. Like,
Yeah,
yeah, it's not at all compressed. The
yeah,
volume is really heavily expressed. I don't know.
yeah.
Instead of using
Al-
a zero, which takes more space, you could just use, I guess, a one. But
yeah,
no,
yeah. Although now that I think about it, I think like a base one system actually maybe technically wouldn't work at all because like I think like the idea of the system is like you have to be able to like write every number as like some digit times the like for decimal you're always able to like you have like something times the ones place, something times the tens place, sometimes something times the hundreds place. Um, but like if you have base one, you're only able to have one possible place because there's one power of one. So like if we require that, like, because I guess if the idea is that like the representation of a number has to have like each place be a different power of the base, then we can't do that with one because there's only one power of one. So we'd only ever be able to represent the number one, I guess.
hmm, right,
Because like the idea is like yeah, like the rightmost has to be uh like one, then the next one is 10, and we have to have different powers for each place, but there's only one power of one.
right. A base one number system wouldn't have powers. It wouldn't have that feature, that capability. Yeah, I,
Yeah,
I guess it could still fulfill its purpose if your purpose is merely to count and keep track of the count. But right,
yeah,
you would not be able to stack it in terms of these powers or exponents.
yeah, yeah, definitely. And I guess I wonder like what the formal definition of like a base something system is, because
Yeah,
I guess if you require different powers for each place, then a base one system wouldn't be possible.
right.
But yeah, I guess if you counted like just putting like however many ones is equal to the number, then that could be sort of a base one system.
Right. I don't know if they ever really explicitly defined what a base is. They kind of gave us an example, but I don't know if there's an explicit definition that would explain why you can't have a base one system.
Yeah, yeah, they don't have an explicit definition.
Hmm.
Yeah. Interesting. But yeah, I guess you can do a base 2, and that's the minimum.
Hmm. Um,
And so with base 2, like I guess for any base, like the base is the number of digits you have available to use. So like with base 10, we could use digits from 0 to 9, and then with base 2, we can use digits 0 or 1, and then like just with base 10, like the places were based on powers of 10. So the rightmost place was the ones place, 10 to the 0. And then the one to the left of that is the tens place, and then the one to the left of that is the hundreds place, and then so on with all the powers of 10, 10 cubed, 10 to the fourth, etc., going to the left. And then with the binary system, it's like the same thing, but like with powers of 2. So the rightmost place is the ones place, which is 2 to the 0. And then the one to the left of that is the twos place. And then to the left of that, we got the 2 squared place, the fours place. Yeah, and then we can similarly expand, like if we write a number in binary notation, like the 11011 down there, 11011 in binary notation, that means like 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 squared plus 1 times 2 cubed plus 1 times 2 to the fourth. And then that subscript 2 going with the numbers to indicate that it's in binary notation. So they're putting the base just to make clear what notation they're using.
right.
And then we have 27 with a subscript 10 to indicate that that's being written in decimal notation. Base 10. Yeah, and then they have like a table of powers of 2. So like the rightmost is the 2 to the 0 place, the ones place, then 2 to the first is 1, so the or sorry, 2 to the first is 2. So yeah, so we got the 2's place, then 2 squared is 4, so the place to the left of that is the 4's place. Then we got the 8's place, then the 16's place.
I see these two different kinds of notation a lot. I don't know if you call them different notations, but in this one, the base is the biggest number to the left, and in this one, the base is the small number to the right.
Yeah. Yeah,
Well,
yeah, exactly.
okay. If the little number is a superscript, I guess that means the base is the big number. And if the little number is a subscript, then it's the base of.
Yeah, I think the idea is that yeah, if you write like a number and it has a subscript, yeah, it's the base, and then the thing that's at the top is like the expansion of it, like kind of writing like what does it mean to say that this number is 11011, and then that like in decimal notation, that's kind of like that would be like 1 times this power of 2 plus 1 times that power of 2. So it's kind of like writing like in decimal notation uh kind of what that means, because it's like a similar idea to like when we had like in decimal notation you would say 27 equals 2 times 10 to the first plus 7 times 10 to the 0. So here they're saying like 11011 in binary notation um equals each digit times the corresponding power of 2. So they're kind of writing an expansion of it using decimal notation and powers of 2. Yeah. Oh, actually, oh, were you saying something? I can't hear you.
Oh, I was muted.
Yeah.
I was wondering if people actually think that way. Like, for example, 3 is 2 to the power of 1 plus 2 to the power of 0.
Yeah.
I get it. It's just interesting. I wonder in what situations that way of thinking is used. It's a pretty neat and tidy way of thinking.
Yeah. Yeah. Well, I guess somehow it has applications like to computer science, like somehow, because I guess like they say that um like computers have like some systems, or there's something like about computers where they're like these signals that can be in two possible states, and then like it's useful to represent
Hmm.
numbers in this way because I guess like, yeah, I guess if you
Oh,
have like a bunch of like, I don't know what they are, but they're like, maybe there's like a bunch of switches that can be in one of two states and you want to use them
right.
to represent a number.
Ooh,
Yeah, then like, yeah, you can have like on represent one and off represent zero, and then you can like, by putting the number into binary notation, then you can represent the number using those things that can be in two states each.
that's pretty interesting. Like, if you had a machine that had, I guess, 4 switches, you could represent all of its 16 possible states as each with its own number. Because the
Yeah,
number would, yeah, like, would describe which switches are on and which ones are off.
yeah, yeah, exactly.
That's
Yeah,
cool.
yeah, I like that. Yeah, and also by the way, so yeah, since 3 equals 2 to the first plus 2 to the 0, the binary representation of 3 would be 1 0,
Would
because it's 1
be,
times 2 to the first,
wouldn't it be
1
one?
0.
Wouldn't it be 1 1?
Oh wait, oh sorry, yeah, you're right, 1 1. Yeah, because 1 times 2 to the first plus 1 times 2 to the 0, yeah. Or oh wait, uh, oh yeah, exactly, because this 2 to the 0 is 1. Yeah,
Hmm. Yeah, you're just adding them together. Hmm. Forgot what my other question was. Hmm. Maybe it'll come back to me.
yeah.
Oh, I think I remember what it was. So this 27 with the subscript 10 is, the 10 is just a sign telling us the 27 is in uh, base 10 and not in some other base like hexadecimal or something, right?
Yeah.
So if you had something written like this, 27 with a little 16, um, what would this number be in decimal?
So I guess that would be, so it would be 2 times 16 to the first plus 7 times 16 to the 0. So 2 times 16 is 32 plus 7 is 39. So I guess it would be 39.
Interesting. Okay, so far I follow along with this chapter. It's not the kind of thought I have all the time, but it's making sense.
Yeah. Yeah, it's cool. Yeah, and then below that table, I guess they make the point that like leading zeros can be added or dropped. You don't have, you can either include them or not. Where I guess a leading zero is like a zero that comes before all of the non-zero digits. Like in decimal notation, 3 is the same, is equal to 0 0 3. You don't need to write the extra zeros before the 3. And then similarly in binary notation, like if you want, you can just additional zeros before all of the ones, or before before the first one digit. So like 1 1 in binary is equal to 0 1 1 in binary.
Okay. I guess what's taken for granted there is that it's always assumed you're starting from left to right, from right to left.
Yeah, in the sense that like the rightmost digit is always like the ones place, and the one after the one to the left of that is the twos place, and you always do it in that way. Yeah.
Makes sense.
Yeah. And then it goes through the numbers from 1 to 9 and puts them in binary notation.
Derive the binary notation for the integers from 1 to 9. The binary notation. Okay. Hmm.
Yeah. So like 1 is equal to 1 times 1. So you just have a 1 in the ones place.
It reminds me of building a truth table.
Oh, yeah.
I think I missed one though. Because this is only 8 possibilities.
Yeah.
Oh, it said from 1 to 9 anyway, as rather than from 0 to 9. But let's see. This would be
Yeah.
3. This would be 6 plus 3, which is 9. So this would be 0 to. Wait. Because wouldn't this be 1, 2, 4? So this would be 7. So to get 9, I have to do that, I believe.
To get 9, I guess yeah.
Okay.
Or, let me see. So you would, yeah. Yeah, exactly.
Hmm.
Yeah, so it's kind of like how if you're like writing decimal numbers, like you first go through all the digits in the ones place. Then once you're out of digits, you put like a 1 in the next place and then a 0 and everything before. And then you do it again. So here it's kind of like you go 0 1 in the ones place, and then you're out of digits, and then you go to like 1 in the next place and 0 everything after that. Um, and but like the systematic reason is that like 1 equals 1 times 2 to the 0, and then 2 equals 2 times 2 to the 1 times 0 plus 0 times 2 to the 0, and then like they can all be written like as expansions in terms of sums of 1 or 0 times the power of 2. And then you write the binary number, um, where you have like the digits are whatever you're multiplying by the corresponding power of 2.
Like, this is a tangent, but do you know why does 1 equal some number to the 0?
Oh yeah, so I guess like any number, I guess any non-zero number to the power of 0 is just defined to be 1. So like 2 to the 0 power is 1, 100 to the 0 power is 1. And yeah, that's kind of how it's defined. But also it kind of makes sense because like think about like if you want to go from 10 squared to 10 to the first power, then you divide by 10, and like 100 divided by 10 gives you 10. Um, or if you want to go like from 2 cubed to 2 squared, you'll divide by 2. 8 divided by 2 is 4. So similarly, by analogy, you can say like if you want to go from 2 to the first to 2 to the 0, you'll divide by 2, and then you'll get 2 divided by 2, which is 1.
Okay, that was a cool. I guess this was like an informal proof.
Yeah, yeah, kind of like an idea of like the motivation behind defining a number to the 0 power to be 1.
Yeah,
Yeah, although I think that officially like 0 to the 0 power is undefined.
0 to the 0 power.
Yeah, because like in that case, it's kind of like
0 to the
Like
1 divided by 0?
yeah, that wouldn't work. And it wouldn't make sense to like have a power of 0 be equal to 1.
Hmm.
Yeah, and also by the way, like a negative exponents, like you don't just keep dividing. Like so like 2 squared divided by 2 is 2 to, or sorry, 2 to the first divided by 2 is 2 to the 0, which is 1. Then you divide by 2 again. 1 divided by 2 is 1/2. And 1/2 is 2 to the negative first power. And then 2 to the negative second power is 1/4, and then it keeps on going. You keep on dividing.
Interesting. That's actually really simple.
Yeah. Yeah, it's a cool system.
Hmm. Let's see. A list of powers of 2 is useful for doing binary to decimal and decimal to binary conversions. See table 2.5.1.
Yeah. Yeah, and those are useful because then like if you're given like for example, if you're given a binary number, then you got to know like what are the powers of 2 so that you can multiply the digits by them and add the results.
So when they say a list of powers of 2, do they mean a list of powers of 2 in conjunction with their decimal form?
Yeah.
I see, like
Yeah,
a map.
exactly.
That is helpful.
Yeah.
Like for whatever reason, I guess, what is it like difficult to just look at 2 to the power of 5 and understand that it's 32? How?
Uh
What would the
maybe I
Siri?
guess yeah, it depends on the person. Maybe some people forget that it's 32 and like maybe it's easier to just memorize it than like go through it and figure it out, I guess.
Right. What? What is the way that you would go through it to figure it out?
Well, I guess you would just like do 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Like kind of multiply it out.
Okay. Do you have to multiply it like in a linear sequential order like that? Like in your mind, there's no other way?
Uh, I guess. Well, I guess you could also do like, I mean, you could do it more quickly and just say like, you know, that 2 squared is 4. So like 4 times 4 is 16, and then you have one more 2 left. So you multiply by 2 and you get 32.
Oh.
Because like 2 to the fifth is 2 squared times 2 squared times 2. So you could like have a shortcut like that, or if you happen to remember that 2 to the fourth is 64, just multiply by 2 and you get 32. 2 to the fifth.
Yeah. Hmm. Right.
Yeah, and that could be helpful. Like if you didn't know what 2 to the 10th was, or actually, well, that could be kind of, well, that could, like if you didn't know what 2 to the 10th was, I guess you could do 32 times 32, but that's kind of hard to do. So it's, um, I mean, you could do that with a calculator, I guess. But
Right.
32 times 32 is hard to do in one's head. Um,
The point is, if
but
you
yeah,
multiply them together, you add the exponents, right?
yeah,
That's nice. That's like, it's just like learning more numbers. Um,
yeah,
yeah. If you do
yeah,
it that way, it's not like particularly more difficult. If you do it that if you think about it in terms of just adding the exponents.
yeah, yeah, exactly. Yeah, that could be a good way of calculating. But it could also be like useful, like if you happen to have like a binary number with like 10 digits, just to remember that, um, or I guess it would actually have 11 digits, just to remember that 2 to the 10th power is 1024 without needing to calculate it.
True. Memorizing this list here would be very useful.
Yeah.
Let's see. Represent 110101 in decimal notation. Okay, well,
Yeah, so kind of but the subscript 2 indicates it's in binary, so the one on the far right is going to be the ones place, and then we'll have the twos place to the left of that, and then to the left of that we'll have the two squareds place, so the fours place, and then to the left of that the eights place, then the 16s place, and then the 32 place. Yeah, exactly. So they'll all be powers of 2. So like to figure out the decimal representation of that, we would just take the digits, multiply them by the corresponding powers of 2, and add.
So we have. Wait a second. You said we would multiply them by the corresponding digits and add?
Yeah, meaning that like we would do 1 times 2 to the 0 plus 0 times 2 to the 1, etc. Or I guess the book does it in the reverse order. The book starts going left to right.
Now let's see, is there an easy way of crunching this number up? Because it's not as easy as multiplying exponents. Like multiplying 2 to the 5th times 2 to the 4th gets you 2 to the 9th. That's super easy. That's really just
Yeah,
addition.
yeah,
In terms
yeah.
of,
And this,
yeah, in this
yeah,
case, it's not quite the same, right? Because we're adding 2 to the 5th to 2 to the 4th to 2
yeah,
to the
exactly.
2nd.
Yeah, and there isn't really a rule for adding numbers that have exponents on them. So we kind of just have to do like what is 2 to the 5th? It's 32, and 2 to the 4th
Right.
is 16. So you just kind of add those numbers.
Okay, okay. I swear there was some equivalence. Maybe they'll bring it up later. Wasn't there something called like, was it factorial?
Oh, like factoring?
I'm not really that familiar with how it works, but
Yeah. Well, you could do something like I mean, I don't know, maybe it would help, but like it would like factor out the 2, like you know that 2 to the 5th plus 2 to the 4th times 2 squared equals 2 squared times 2 cubed plus 2 squared times 1, but
right.
yeah, I don't know if that would help necessarily though. It might be easier to kind of just know what 2 to the 5th is and just like add the numbers.
Yeah, maybe so.
Yeah. So I guess in this case we'd have like 32 plus 16 plus 4 plus 1.
But there's some relationship between 32 and 16 and 4 and 1. It seems really tempting to find like a pattern that make it easier to convert binary to decimal.
Yeah. Yeah, maybe.
I don't know.
Yeah, I'm not sure. Yeah, it's possible.
Hmm. Yeah, I'm not sure. I don't have enough tools yet to be able to sit down and tinker with a number like this. Um,
Yeah. Yeah, but I guess in chapter 4 we'll be doing number theory, so maybe that'll give us the tools to figure out another method.
right. Yeah, I'm not sure. Okay, let's
Yeah.
see. Huh.
Yeah, and then the thing below is kind of another way of representing the same thing. So they just kind of like next to each digit they wrote the power of 2 that it corresponds to and what that equals in decimal notation. And then they like figured out what each of the digits come like they multiplied each of the digits by the powers of 2, and then they added all of them. So they kind of this is kind of like another way of representing it.
What's this 32 over 53?
Oh, the bar is just like like the sum of all of these is 53. So sometimes like
I see, I
people like
see.
write, yeah, they should have written a plus sign though to indicate that that's what they were doing.
So represent 209 in binary notation.
Yeah, so that's trickier going in this direction. Like, so I think what we got to do is like, we've got to like find the biggest power of 2 that's less than 209.
Yeah, the same idea.
Yeah.
Let's see. How quickly can we find that? If you just memorized it, then that's one way to do it. Um,
Yeah.
I think each one is half as big as the one that comes after it, right?
Yeah. Yeah, exactly.
Let's see. Well, I guess we could just cheat and use this chart here. So 128 is the biggest one that's less than 209.
Yeah.
So the number is probably going to include 128 as well as. Now, I don't know why I know this to be true. It may or may not be true. But I just assume it'll always include the biggest number it can.
Yeah.
While not busting the sum, the
Yeah.
running sum. I wonder why is that the case?
Yeah. Yeah, I think it's yeah, it's true. And but like why? I guess well, it's like I guess like I think it might say in the book that like later in the number theory section they're going to prove that you can write every number as like a uniquely as a sum of like ones and zeros times powers of 2. So like for any number there's like exactly one way to write it
Oh.
as yeah, as like a sum of ones and zeros times powers of 2. And like that sum is always going to include like uh it'll include like the biggest possible power of 2 that's less than the number, or that's less than or equal to the number, and then it'll include the next biggest that's less than or equal to what we have left. And yeah, so I guess that there's like a way of proving it that'll use number theory.
Yeah, at the very least, there's always a most optimal way of doing it with the least like duplicates of the power of 2. I guess in with
Yeah,
powers of 2, you might not ever need a duplicate.
yeah, yeah. In fact, yeah, I guess you won't. Yeah, you won't ever need a duplicate. I guess it's always going to be like different powers of 2, and you're figuring out kind of what whether a 1 or a 0 goes with each of them.
So every number is like assigned a unique sequence of values of 2, like a unique combination. Every number
Yeah,
has its own.
yeah, yeah. You need a combination of like ones and zeros multiplied by powers of 2 and added together.
I guess that should make sense since every number would look unique in its binary form.
Yeah,
Yeah, and its binary form is just another representation of these powers of 2. So that means
yeah,
that every number would have a unique combination of powers of 2.
yeah, yeah. Exactly.
Oh.
Yeah,
So what were we doing? 209?
yeah. So we know that 128 is the biggest power of 2 that's less than or equal to 209, and then so we've done part. So now we'd have to subtract 128 from 209 and see what we have left, and then we'll add the power of 2, the biggest power of 2 that's less than or equal to what we have left.
So let's see. 209 minus 128 is, well, 209 minus 128 is 81. So that
Okay.
means We could squeeze in 64 as well then.
Yeah.
Which leaves us with 17. So we could squeeze in 16, which is.
Yeah, 2 to the 4th.
And then
So that means, and by the way, that means that we're going to have a 0 times 2 to the 5th.
0 times 2 to the 5th. True. Lastly would be 2 to the 0. So, like you're saying, then the full number is going to have, I guess it'll have 7 digits.
Yeah. Yeah, and then the leftmost will be the 2 to the 7th place.
Yeah.
1, 1. Yeah. Yeah. Oh, and actually we have we have an additional 0 before the 1 because I guess like since we're going up to 2 to the 7, we actually have 8 digits because 2 to the 0 is included.
2 to the 0 is included. So,
yeah.
I see.
Yeah, so we'll have zeros for the 2 to the 3rd power, the 2 to the 2 power, and the 2 to the 1 power.
Makes sense.
Yeah.
Yep. All right, let's see. Binary addition and subtraction. The computational methods of binary arithmetic are analogous to those of decimal arithmetic. In binary arithmetic, the number 2 equals, let's see, 10, or no, equals
Yeah.
1 0 in binary.
Yeah.
Plays a role similar to that of the number 10 in decimal arithmetic. Example. Add 1101 and 111 using binary notation.
Yeah. And then there's some more, like in the solution, they give us some more information that we need to do it.
Let's see. My first guess would be to add it the way you might add in decimal, except you carry the 1 after the sum of each column exceeds 1 as opposed to exceeding 9.
Yeah.
So we have 0, 0, 1, 0, 1.
Yeah.
Looks like, I wonder how they did it here.
Yeah. Well, yeah, that's how they did it.
Except they didn't. Oh, they did actually here.
Yeah, they were just pointing out like some other things beforehand.
I see. So, I caught that pun. I think that was a pun, right? Some
Oh,
other
was it?
things. They were pointing out some other things. I mean, maybe that was a no pun intended moment.
Oh, yeah. Oh, I didn't realize that. Yeah. Wow, interesting. Yeah. Yeah, it was a good catch.
Hmm.
Yeah. 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 So that's cool how it works similarly to like decimal arithmetic.
Yeah. It's like we're just reviewing the concept of a number system right now.
Yeah. Yeah, and an interesting thing is like it's not initially clear how this relates to what we were doing earlier with logic. but
Uh,
it's gonna end up related.
right. It's not clear, but looks it looks the same. Like all I can see that there's ones and zeros involved, which are very like true and false.
Yeah,
But I don't know what connections they're gonna make.
yeah,
Subtract 1011 from 11000 using binary notation. Um, okay. Subtraction. So let's see. I don't remember the kindergarten way of subtracting. I would just assume you like reverse carry the run. You subtract the one instead.
yeah, yeah. It's kind of like that. I actually also had forgotten. So I looked at it. And it's like involves borrowing. So it's um, like if those were decimal numbers, then you would so then you have like 0 - 1 and 0 - 1, so you can't uh have like a negative. So like you'd have to you'd borrow a 1 from the 10 and turn it into a 9.
The thing is,
And
like, it's so much more expensive of an operation because each time you borrow, you kind of have to trail all the way up the digit tree here. Like, since my zero here is being subtracted from, I have to subtract from this one. So I have to subtract from the one to the left of that. And I have to keep subtracting to the left until I don't have to borrow anymore. So let's
yeah,
see here.
yeah. So like the you have 0 - 1 in the leftmost part, so you got to borrow a 1 from from the previous 0 and turn that into a 1. Going imagine going from a 1 0 to a 1, and then the in the rightmost column the 0 becomes 1 0.
So let's see.
Or I guess, yeah, I guess you can actually kind of see how far back you have to borrow and start there.
Wait a second.
Yeah, I think. Well, I guess.
I think this might be like this. Wait, no. Like, hmm.
Yeah, I think it's um. So when you're in the rightmost column, you have 0 - 1, and you can't just kind of do that because then that would be a negative. So you have to imagine the 0 to the second 0 from the right was a 10 and was a 1 0, and then you borrow a 1 from that and turn it into a 1, and then you give that 1 to the 0 on the rightmost 0 to make it 1 0.
You give it to make it 1 0. So you would have one. Oh, wait a second. To make it 1 0.
Yeah, so the rightmost 0 turns into 1 0.
So 1 0 minus one, right?
Yeah,
Which would be one in binary because 1 0 is two.
yeah, yeah. So we end up with a 1 in the rightmost column of the difference. But then for that second to the right 0, that one to make that into 1 0, so that we would actually have had to have borrowed from the other 0 to the left of that.
So what about 1 0 minus 0?
that would be 1 0 minus 0. I guess that'll be 1 0, but we'd actually, I guess we have to like,
Do you
but
just
then we
give it
can't do that
back?
because yeah, we need to have just one digit in the difference. So we got to borrow. Uh oh wait. Uh 1 0. Uh, oh wait, I guess so. Oh well we uh I guess so. So yeah. So on the rightmost, and here I'm just kind of looking at it because I, yeah, this is kind of more confusing part. The the rightmost. Uh, mm, so it looks like what they're doing is the. So I guess yeah, starting it again from the. So the right, like the rightmost column, you've got 0 minus 1, and we know we can't do that. So we need to imagine borrowing from the previous 0. But the previous one there, that's actually a 0, so we can't borrow. Like we need that previous 0 to be a 1 0 so that we can borrow a 1 from it. Um, to make that previous 0 1 0, we need to have borrowed from the previous 0, but that would also need to have been a 1 0, so we need to borrow from the previous 1, I guess. Um,
And then that
yeah,
one
this is the
is,
hardest part.
yeah, this is definitely like the crux of the chapter, I think.
Uh,
Well, I don't know. It's just a mechanical thing, but I would like to understand this.
hmm. Yeah. Well, let's see. So I guess yeah. So starting at like okay, so the rightmost column we've got a 0 minus 1. We can't do that, so we need to borrow from the previous row. But there's nothing to borrow from a 0, so we need to have borrowed from the previous column. But there's nothing to. But in the third column again, there's nothing to borrow from a 0, so we need to have borrowed from the previous. Oh no, but the previous, yeah, we need to have borrowed from the 1 1 at the beginning. Uh, so we can just cross out the 1 1 at the beginning um, of the first thing of the 1 1 0 0 0. So we can cross out the 1 1,
Okay.
and the 0 to the right, the 0 to the right of the 1 1 is going to borrow a 1 from the 1 1. So the 1 1 is going to become 1 0. So you can write a 1 0 above the 1 1. And yeah, or I guess might work better to kind of have it like right above the 1 1 to indicate that like, oh yeah, you could also do that. Yeah, it's like the, because yeah, we're gonna have a 1 0. The 1 1 turns into a 1 0 because the 0 to the right of it needs to borrow a 1, and so next to the 0 we can write 1 0, or we can write a miniature 1 to indicate we have 1 0 now. Yeah, but then the 0 to the right of that needs to borrow a 1 as well, so then we cross out that 1 0. And so then 1 0, it's losing a 1, so it just becomes just plain 1. So we're going to have like that 1 0 in the third column is going to become just a plain 1.
The third column?
Yeah, the one that's 0 minus 0. So like the 0 at the top, it became a 1 0 when it borrowed a 1, but now it is itself kind of donating a 1. So
Right.
it turns into 1.
Oh, interesting.
Yeah. And then that 0 in the next column, that borrowed a 1 to become a 1 0. But then the 0 to the right of it also needs to borrow a 1, so that 1 0 in the second to the right column becomes a 1 as well. And then the 0 and the rightmost 0, it's borrowing a 1, so it becomes 1 0.
So that was just to subtract 1 from this number, right?
Mm.
We
Yeah, well, when we're borrowing a 1, I guess we're subtracting 1 from whatever whatever digit we or whatever we've got.
like
Oh, yeah, to subtract a 1. Oh, yeah. Oh, that's interesting.
so let's see here. I guess maybe first we should just understand the high level and then see if we can implement it. So with this subtraction,
Yeah. Yeah, no, that's harder to understand. I guess yeah, I mean that like I just knew that because I was looking at it. But um that well, I guess the mechanism is like if you have like a 0 minus something, you can't do that. You have to borrow a 1 from the previous thing. And then if that previous thing itself is a 0, then you need to borrow 1 from the previous thing before that, and they keep on borrowing until you get to a 1 or like a 1 1 or something. Um,
hmm. Well, like, even before using the language of borrowing, I just want to know, like, I want to review um, how calculating subtraction works.
yeah. Well, in terms of calculating, it's kind of like we subtract the top from the each top digit from a bottom digit, but then like you borrow to like make that work.
Right,
So that you
like
have like one digit in each column.
that, like you're right, that overflow mechanism. It seems to be like if you have a sequence of digits and you take you take from a digit that is at the base of the system, like it's the lowest digit the system has, then the digit like the next greatest digit would decrement, and the digit that you were originally decrementing would become the greatest possible digit. Like if you had 90 minus 1, you would end up with 89.
Yeah.
So let's see. Hmm. 90 minus 1 ends up with 89. I guess, like, why do you end up with a 9? I guess it's like there's like an imaginary, like, 8 plus 10. So that's 90. Well, 8 in the tens place plus 10 in the ones place would be
Yeah.
90. And so subtracting 1 from the ones place will get you 8 plus 9, which is 89.
Yeah. Yeah. Yeah, and I think that kind of idea is involved in carry or in the borrowing.
So if you have like 110, which I guess would be 6, 6. If you subtract 1 from 6, you should get 5. Let's see.
Yeah. Yeah, actually, yeah, this is a good way of example to illustrate because, like, or actually, yeah, because like what you're doing when you borrow the one is kind of just like writing the number in a different way, sort of, because it's
Right.
like, yeah, it's like if it's kind of like, um, so from the zero you borrow a one, uh, uh, from the one, I guess,
From the 0. So,
in terms ones, yeah,
yeah, you
yeah,
rewrite the number so that subtraction can continue.
yeah, because it's kind of like you're saying, you have a one in the two in the fours place, you have a zero in the twos place, and you have a 1 0 in the ones place, and that's the same as having a one in the fours place and a one in the twos place. It's just like kind of a you're changing it so that you can have a two-digit thing in one of the places so
Right.
the subtraction works.
So in this case, we have 6 minus 1. So in the ones place, we need um, 2 to subtract from.
Yeah, yeah, and then we'll do that by like taking away um a one from the previous place.
Right. So we basically have 4, like, and 2. Wait, no. 4 and I guess it would be 4 and 2. We would still have our like digit in the fours place.
Yeah, yeah, yeah. We'd have like the original representation 1 1 0. That's like 1 times 4 plus 1 times 2 plus 0 times 1. And then when we're doing the borrowing, then we pretty much have 1 times 4 plus 0 times 2 plus 2 times 1.
Whoa, this is kind of tricky to express in binary here.
Yeah,
Like what I'm trying to say here though is when we're doing the carrying, we have this number, which is 4, because there's a 1 in the fours place, a 0 in the twos place, and
1 0 in the ones place.
exactly.
Yeah. Yeah, because like a 1 0 in the ones place is just the same as having a one in the twos place.
1 0 in the
Or yeah, because it's like,
yeah, it kind of it. I mean, it's apparently it is. So let's see. Now we're gonna subtract 1 from that. So this is gonna become this. So we'd end up with this. Since we're subtracting something, we'll never end up in a state where we have two digits in one digit's place.
Yeah.
It's just like a temporary technique.
Yeah.
So
Yeah. Yeah, that's cool. Actually, that's something I never realized before about ordinary like decimal subtraction. Even yeah, I kind of just mechanically applied the method without understanding how like what was being done.
yeah.
Yeah. Yeah, and 101, that's what we want because that's 1 times 2 squared, which is 4, plus 1 times 2 to the 0, so plus 1. So 4 plus 1 is 5.
Right? Maybe you can do. No, we can't like do subtraction in some easy way like that because 2 times 4 like minus 2 times 3 doesn't equal anything like predictable or neat within our,
Yeah.
it would have to be divided in order to do it that simply. So let's
Yeah.
see. Hmm.
Yeah. Yeah, and then we can also do it for like so like the for the example we have all of the borrowing done and then we can do it similarly.
Say that one more time.
For the example 11000 minus 1011, we've already done all of the borrowing. So now we can like similarly do the subtraction.
In in
Like under thus the addition. Um
right.
yeah.
I think that I'm still pretty weak here though. Like I don't feel super confident uh, in my proficiency at subtracting in binary.
Yeah. Yeah, it's hard.
Yeah.
Yeah. But yeah, I guess the general method is like just if you ever have it like the mechanical method is like if you ever have a 0 on top, you got to borrow a 1 from the previous column. And if that column itself has a 0 on top, you got to borrow, yeah, got to keep on borrowing and keep on going to the left until you get to a 1. So like in the thing at the difference at the bottom there, like for the rightmost row, we've got a 0 on top. So we got to borrow from the previous row. And that has a 0 on top. So we got to borrow from the previous row. That also has a 0 on top. So we got to borrow from the previous row. And then that row, the one like the second to the left to the far left, that has a 1. So we can just borrow that 1, turn the 1 into a 0. And then when the 0 in the third row borrows the 1, it becomes a 1 0. And then but we're borrowing from that third row too, so the 1 0 has to turn into a 1 because 1 0 minus 1 is 1. And then the second to the right row that borrowed a 1, so it becomes a 1 0. But the final row on the right, that's also borrowing, so that 1 0 in the second to the right row turns into a 1. And then the rightmost row it borrowed a 1, so it became 1 0. And then now that gives us something where we can do all of the subtraction,
Right.
and just have 1 digit per spot.
Hmm. Yeah, maybe it's not so complicated if you think about it in terms of like a floating 1 0, which you can then subtract 1 from.
Yeah.
Let's see.
Yeah.
So
Yeah, exactly.
what about 7 minus 3? I guess that would
Mm,
be
that would be one 1 1 1 minus 1 1. 7 is 4 plus 2 plus 1. So you'd have 1 corresponding to every power of 2.
okay. This is pretty easy.
Yeah.
So
Yeah, that one you don't need to borrow anything.
what about 4 minus 3 then?
So 4 is going to be 1 0 0 because it's 4 plus 0 plus 0. So we're going to have 1 0 0 minus 1 1. Oh, yeah, and there we got to borrow.
You would think the answer would be
Yeah, so you should end up with 1. And
I'm ending up with 2 1s though. Because
oh, yeah, well,
like
oh, go ahead.
the 0 minus 1, so we have to turn the 0 into a 1 0. And then
Yeah,
to the left of that is another 0 minus 1, so we have to turn that 0 into a 1 0.
yeah. But the thing is that like we turn the zeros into 1 zeros by borrowing from the row column to the left. So like so it's like so we have on the rightmost column we've got a 0. So we're going to turn that into a 1 0, and we'll do it by borrowing from the previous column. But the previous column also has a 0, so that previous column also needs to borrow. So so the middle column, it's borrowing from the column with just a 1, so that 1 turns into a 0, and then the 0 in the middle turns into a 1 0. So we can start out by like kind of putting that part. We can cross out the 1 in the 1 0 0, and then put a 1 0 in the middle. Yeah, so that 1 just becomes a 0. Yeah, and so now we've got 1 0 because the middle column borrowed from the 1. So now we've got a 1 0 in the middle, but the rightmost 0 also needs to borrow. So it's going to borrow from the 1 0 that's now next to it, and then that 1 0 is going to turn into a 1.
Okay, so not only do we subtract the 1 0 from what's being subtracted from it, but we also subtract what's being borrowed.
Yeah.
So it
Yeah,
isn't
exactly.
in that little center column, it's not just 1 0 minus 1, which is what would give me this 1 here. It's actually 1 0 minus 1, but also minus what's being borrowed.
Yeah, exactly. So you can like cross out the 1 0 and write a 1 because that's what happens when you like subtract the what's borrowed from it.
And then you do the subtraction.
Yeah.
So
Yeah.
it's like 2 is subtracted from it mechanically.
Yeah.
Huh. Okay.
Yeah. Yeah, so that's what's going on with this subtraction. And then like we end up with in the rightmost like a 1 0 minus 1, etc.
Hmm.
Yeah. Oh, but this is interesting. This is where the logic comes in.
Let's see. Circuits for computer addition. Consider the question of designing a circuit to produce the sum of two binary digits P and Q. Both P and Q can be either 0 or 1, and the following facts are known. 1 plus 1 is 1 0. 1 plus 0 is 1, which is 0 1. 0 plus 1 is 1, which is also 0 1. 0 plus 0 equals 0 to 0, 0. It follows that the circuit to be designed must have two outputs. One for the left binary digit, this is called the carry. One for the right binary digit, this is called the sum. The carry output is 1 if both P and Q are 1. It is 0 otherwise. Thus, the carry can be produced using the AND gate circuit that corresponds to the Boolean expression P and Q. The sum output is 1 if either P or Q, but not both, is 1. The sum can therefore be produced using a circuit that corresponds to the Boolean expression for exclusive OR. P or Q and not P and Q. Hence, a circuit to add two binary digits, P and Q, can be constructed. This circuit is called a half adder. So,
Yeah. So that's worth discussing.
Yeah, a circuit which adds two numbers. I guess
Yeah.
two numbers, P and Q. These seem to be like, I don't know if they're single digit numbers.
Yeah. Exactly. So each of them is either a 0 or a 1 in binary.
Okay. And the half adder has like its own truth table to solve this, which is like,
Yeah, it's like well, so yeah, you have the two inputs, the P and the Q. Each of them is either a 0 or a 1, and like these sums that are written there, that's where the truth tables come from. So, um, the circuit is gonna have two inputs, the two digits that it's adding, and then it's gonna have two outputs, the two digits of their sum, or of like what you get when you add them. So the
you're right.
uh yeah, but I guess I avoid calling it a sum because they also call the right binary digit the sum. Um, but
Right.
yeah, but yeah. So there's like a pattern um, that if you're adding two ones, that's the only case where you get a one as the leftmost digit. In the when you add them together. So um, so like it's kind of like you input the P and the Q, and then you do one thing to them to get the left digit of the binary digit, the carry, or no, the oh wait, I guess so oh yeah, yes, so the carry, exactly, the carry is only one when both P and Q are one, and then also by observation of those sums, the sum, the rightmost digit of when you add them together is one, just when one of P or Q is one, but not both.
Hmm.
So it's like we're gonna so we'll have the two outputs, the carry and the sum, and then to get the carry, we're gonna put the P and Q through an AND gate because the carry is one just when both of the inputs are one, and that's how an AND gate works. And then to get the rightmost binary digit, we know that it's one just when one but not both of P and Q is one. So we're gonna need to like put to get that part to get that output, we're going to need to put P and Q through some kind of combination of gates that amounts to an exclusive OR.
Right.
Like one of them is true, but not both. So we're going to have like, it's going to involve like an OR gate, and then it's going to like, I guess it'll have like, it's going to involve like multiple gates, like the OR end and a not and another end.
Right. Hmm. In in XOR gate. Oh, wait, what kind of gate is this? Yeah, an exclusive OR gate.
Yeah. Although I guess we don't have like we, I guess the exclusive OR gate is like there isn't like one gate that functions as exclusive OR like we have that we have available to us. So we kind of like need to make an exclusive OR using a combination of OR and a NOT gates, it looks like.
Yeah, it would be like A or B and not both.
Yeah.
So let's see. We have P and Q. We need P and Q. No. We need P or Q. Um,
Yeah. Yeah, we kind of I guess we have to do like a soldering of wires. Like we're gonna need to like have we're gonna have like the P and the Q go through an OR gate. Then we'll also need to have them go through an AND gate and then a NOT gate. And then we'll have the results go through an AND gate.
right. Oh wait, and not both. So that's the AND gate. But I guess it's actually a NAND gate.
Yeah. Yeah, exactly. Which would be like the AND gate followed by a NOT gate.
Okay.
Yeah. Yeah, and then they illustrate it below as well. And the one they have below, like it puts like both out so that it has both of the
Oh,
outputs. So we'll have like
the and okay is the carry.
yeah. So we want to have like one output that comes just from the two of them going through an AND gate. But then like as one of our ingredients of the sort of exclusive OR gate, we also have them going through the AND. So we're going to have a soldering after the AND that kind of continues them on to the exclusive OR process.
Yeah, I see. Hmm.
Yeah.
There's something about that that's pretty cool. That you can like what's the word I'm looking for? I don't want to say sum up addition in terms of a truth table. It's like the implementation of addition of two single digit numbers to produce at most a two-digit number was solved using a truth table.
Yeah. Yeah, it's cool.
Hmm. Yeah, the truth table lays out all the possibilities. Hmm.
Yeah. Yeah, it's interesting. And I guess maybe like in real life computers, like this kind of stuff is going on, but like a very like an even more complex level, like many of these going on at once, like for each thing you write on the computer, like and like each pixel and like everything.
Right, it's been thoroughly mastered.
Yeah.
Hmm. Interesting. I like that way of thinking. I wonder what else can be applied to like solving a process, a methodology, like using a truth table. You're not even really looking at the particular numbers anymore. You're looking at the truth table of the operation of
Yeah.
what the possible outputs could be. I don't know if that's exactly articulated correctly because there's infinite numbers. So a table couldn't tell you all the possible outputs. But just like there's infinite statements that you could make. But I guess there's not infinite something.
Yeah.
Maybe there's not infinite outputs for single digit addition. In fact, perhaps there's only four. Or perhaps there's only, yeah, four.
Yeah. Yeah, I guess there are only four, but I guess the more complicated editions, you could have like huge numbers of possible outputs.
Yeah, most likely. Um, when dealing with binary, I guess, like, what if you had P, Q, and R? I mean, I guess, first of all, you would end up with eight possibilities.
Yeah.
Two, one, two, three, one, two, oops. Oops. And then so I guess it's a little different than a half adder. Half adder has a carry and a sum bit. This would have something else.
Yeah. Yeah, and I think they're gonna do that in the next part.
Oh, really?
Yeah. Yeah, that one involves a full adder, apparently.
A full adder. I don't know. I wonder how it's gonna turn out. I mean, from this, it just looks like you would have. I don't know what you call it. Like a carry, a sum one, and a sum two, but maybe that doesn't make sense. Um, a carry, like at least you would have a four's place, a two's place, and a one's place.
Yeah. Yeah, you would. And I guess there would be like more complicated logic to like you have to like look at what the patterns are. Yeah,
Hmm.
and I guess in fact, like it looks like the next thing they do is like look at not only adding three binary digits, but like adding two binary digits, each of which has more than one digit. And then that ends up involving like requiring a mechanism for adding three digits.
Oh,
Yeah,
which
it's
one?
going to be like, yeah, it's like making a circuit that could add like 1 1 and 1 0, for example. And then like when you're doing addition like that, you're going to need to carry a digit up, like carry a one, and then you're going to be adding three digits. So like as part of the method for figuring out how to add multi-digit
Right,
binary numbers, we need a mechanism for adding three binary digits.
right. I guess this might still be um half adder logic because it's like adding three single digit numbers. Well, at least that's what I was getting at, but it looks like they
Yeah,
didn't explain. I don't think, yeah, that was going to get the right answer though. But I think
yeah,
they're about to explain.
yeah, yeah. Because I wonder if I don't maybe like if you're adding three digits, you could just like put the first two through the original the circuit that we already have, and then just add in the other one.
Oh,
Yeah, because you can just do P plus Q, and then you can do the result plus R, and then you just take P plus Q and R and put them into the original circuit. So you just kind of like have the circuit like what we had earlier twice, I guess. And like the
Wait.
out, yeah, like you plug in the P and the Q, and then you just like take that as an input together with R, and then put it into another one.
So the P and the Q get you an output of a carry and a sum. So what would you
Yeah.
do with that carry and sum?
Oh, right. Oh, yeah, I guess. Oh, yeah, that's the tricky. That's the issue, because yeah, that's not going to be a single digit. So yeah, I guess that's why we need a more complex method. Yeah, I wonder what they do.
Hmm.
Yeah, so we can check out that part.
Yeah.
Yeah, I guess I can read this one. So now consider the question of how to construct a circuit to add two binary integers, each with more than one digit. Because the addition of two binary digits may result in a carry to the next column to the left, it may be necessary to add three binary digits at certain points. In the following example, the sum in the right column is the sum of two binary digits, and because of the carry, the sum in the left column is the sum of three binary digits. So here we're doing 1, 1 plus 1, 1. And looking at the right column, we have a 1 plus a 1, and that's 1, 0. But we can't fit 1, 0 into the bottom there, so we've got to carry a 1 up. And then we end up with 1 plus 1 plus 1 in the next row. And that's going to give us 1, 1. So like if we're going to come up with a mechanism for adding multi-digit binary numbers, one thing that we need to do is come up with a way of adding three binary digits, because that's going to come up sometimes when you're adding multi-digit binary numbers, like it does in the leftmost column there.
Makes sense.
Yeah. So thus, in order to construct a circuit that will add multi-digit binary numbers, it is necessary to incorporate a circuit that will compute the sum of three binary digits. Such a circuit is called a full adder. Consider a general addition of three binary digits p, q, and r that results in a carry or leftmost digit c and a sum or rightmost digit s. So p plus q plus r equals cs. I like how they did CS because it relates to computer science.
Right.
Yeah. So the operation of the full adder is based on the fact that addition is a binary operation. Only two numbers can be added at one time. And thus, P is first added to Q, and then the Q is added to R, or no, and then the result is added to R. Um, so for instance, consider the following addition, and then it gives an example. So So on the next page, we got um, 1 plus 0 plus 1. So like when you add, you do two numbers at a time. So like you do 1 plus 0, and that's just 1. Or if we're writing everything with two digits, so it'll be 0, 1. And then we'll add 1 to that. So it's going to be 1 plus 1, which is 1, 0. So the whole sum is 1, 0.
Hmm.
Um, So the process illustrated here can be broken down into steps that use half-adder circuits. So I guess the first step would be the easiest. Like we're starting out with two binary digits, p, and we're doing p plus q plus r. So first we do just p plus q. We can just do that with a half-adder, which we already did earlier. So p plus q, use a half-adder, and we'll get something with two digits, c1 and an s1, the carry and the sum. Now we've got to add r to that, r, c1 s1 plus r, and then we need to do something more complex to do that. And to do that, we have to do, so add r to S1. So we're doing the first column of that sum, C1 S1 plus R. So we got just 2 digits here, adding R to S1, so we can use a half adder to do that. So S1 plus R, it's going to be something, and they call it C2S. It'll have 2 digits. And then, interesting. So then S is going to be the rightmost digit of the entire sum of P, Q, and R. Yeah, and then we got to figure out how to deal with the C2 and C1. And then we got to determine the leftmost digit, which they call C, of the entire sum, as follows. First, note that it's impossible for both C1 and C2 to be ones. For if C1, so like they're going to say, like, imagine that that C1 and C2 are both ones, and see how that would lead to something impossible, like a contradiction.
Right.
So they're kind of doing like a mini proof here. So C1 and C2 can't be both be ones, because if C1 equals 1, and C1 was the leftmost digit of P plus Q. So if C1 equals 1, then P and Q are both ones. And that's because so P plus Q equals C1 S1. We saw earlier that we only get a leftmost digit of 1 if both of the binary digits are ones. That's why we use an AND gate for the carry.
Mm-hmm.
So if C1 is 1, then P and Q are both 1. And if P and Q are both 1, then that means that S1 is 0. Because then P plus Q is 1 plus 1, which would be 1, 0. So C1 S1 would be 1, 0.
So C1 and S can't both be 1.
Yeah, exactly. Yeah, so they just prove that. And then consequently, the addition of S1 and R, that gives us a binary number, which they call C2S1, where C2 equals 0.
Now, what about that line?
Yeah, think about that. Wait, so they're saying that so S1 and S2 can't, or C1 and C2 can't both be ones.
I
So
see why the carry and the sum can't both be 1. Because if the carry is 1, then that means that both the elements being added were 1, which means the sum would be 0.
yeah,
So why can't C2 and C1 be 1? What what
yeah.
is C2?
Yeah, I think it might be helpful to maybe, like, because the book kind of puts it on 2 pages, which makes it confusing. So maybe we can write like everything on, like, on
Right.
one page here. So I guess I'll go. So I guess we have P. So firstly, P plus Q equals C1 S1,
Right.
and that can maybe go like on the left of everything.
C1, it's like C1S, right? Or they call it
Uh,
C1S1? That makes more
yeah,
sense.
C1 S1. Yeah. In this case, it's just it's a S1, and then the S comes later. Yeah, so P plus Q equals C1 S1, and then S1 plus R equals C2S. And I guess they already got that part there. Uh, but
S1
so
plus R. S1 isn't even the sum of the number, right? It's just the rightmost digit of a two-digit
yeah,
sum.
so it's like when you're doing C1, we want to do C1 S1 plus R, and then we're going to be doing S1 plus R in the right column of that. Yeah. So I guess we saw firstly why C1 and C2 aren't both 1. And so we got that. And then the next part is that it says that S1 plus R
Equals C2S.
gives us, it says C2S1.
Okay.
But I think maybe that's a typo because like over there it says C2, like above up there above everything it says C2S.
Right, right.
Yeah, so I guess that was a typo. So S1 plus R equals C2S,
Okay.
where C2 equals 0. Because well that's if S1 equals 0, I guess. Um,
So it
um,
should be S2, right?
uh, I guess I'm not sure if they have an S2. I think they just called it yeah, it would be nice if they said S2. They just called it S for some reason instead of S2. But yeah, we could call it S2, I guess. Um, so they're saying, so they said that C1 and C2 aren't both 1. And that means that, I see that. Okay, so like S1, or no, actually, C1 and C2 aren't both 1. S1 plus R. I don't know why S1 plus R. Why does C2 have to be 0?
Yeah. Let's see.
Um,
C2.
because yeah, I mean, FS, I guess they're saying, I guess maybe they're just looking at the particular case where S1
Huh.
equals 0. Because if S1 equals 0, then yeah, C2 is 0, because then you're going to have either 0 plus 1 or 0 plus 0.
Let's
Because,
say
like,
S1 is 0 and C1 is 1. So it's like a case where P was 1 and Q was 1, so you ended up with 1, 0.
yeah,
You can either add 1 or you can add 0, right?
yeah,
And in both cases, C2 would be 0. Wait, let me see if I'm getting this right.
yeah. I think, yeah, I'm not sure. I think they might be considering, like, they're saying, like, firstly, C1 and C2 can't both be 1. So maybe they're like starting up, like maybe they're like considering two cases, and like the first case is uh like what if C1 is 1 and C2 is 0? Then what? No. Yeah. Uh, uh,
I gotta make sure I know it.
wait. Yeah. Oh, never mind. I think they're showing that this is still part of the proof that C1 and C2 aren't both 1. So they said first that like if C1 is 1, then S1 is 0. Uh yeah, which we got that, but like then that, so given that S1 is 0, then S1 plus R is going to be 0 plus R. So it's either 0 plus 1 or 0 plus 0. And that's going to give you a one digit thing, either a 0 or a 1. So like S1 plus R equals C2S. C2S is going to be either 0 or 1. So the leftmost digit, the C2, is going to be 0.
You say C2S is going to be 0 or 1?
Yeah, yeah, because so like going through the lot, yeah, I missed that that was part of like they probably should have organized the proof better, like by paragraph, multiple paragraphs. But like, so the first thing they want to show is like C1 and C2 aren't both one. Um, so to prove that, they have multiple steps, and the first step is like, well, assume that C1 is one. We're going to show that C2 couldn't also be one. So assume that C1 is one. C1 comes up in like the sum of P and Q. P plus Q equals C1 S1. If we have a 1 at C1, then the P and the Q have to both be 1, because like 1 plus 1 is 1 0. But if we had 1 plus 0, 0 plus 1, or 0 plus 0, we would have 0 1 or 0 0. So the C1 would be 0. So yeah, so we know that in that case, S1 would have to be 0 if the C1 is 1, because the only way you get a 1 for the left digit of the sum of two binary digits is if you end up with a sum of 1 0. So
Right.
we know that it's supposing that C1 is 1, we concluded that S1 is 0. So um and then we also have, well, S1 plus R is what we'll call C2S. Um and so we saw that S1 is 0, so we're going to have 0 plus R equals C2S. Um, and well, R is a binary digit, so R is either 0 or 1. So S1 plus R is going to be either S1, that's going to be 0 plus 1 or 0 plus 0.
Can you
Um,
restate this point?
yeah, yeah. So, like, so you got the first step, right? Like, the first step, we suppose that C1 is 1, it follows that S1 is 0.
Yeah, that part makes sense. Easy to follow. What about this
Yeah,
next part?
yeah, the next part, like, so we showed that S1 is 0. If so, like, we're still working under the supposition that C1 is 1, so we showed that S1 is 0. Now we look at the next equation. S1 plus R equals C2S2, or C2S. um so we have S1 equals 0, so we can just substitute, and then we have 0 plus R equals C2S. Because like in this scenario, we showed that S1 equals 0. So S1 plus R equals is 0 plus R.
Okay.
Yeah. So 0 plus R equals C2S. Um, and so R is like the S's and the R's and all of these variables, they all represent binary digits, meaning that they all have a value of 0 or 1. So
If it's 0 plus R, then C2 must be 0.
yeah,
So
yeah,
C2 must
exactly.
be 0 whenever C1 is 1.
Yeah. Yeah, so then that proves that like they can't both be 0. So that completes the proof of that part, which I guess they're going to use um for to reach further conclusions. Yeah, so they've demonstrated that C1 and C2 aren't both 0. Um, next, observe that C. Oh, and then there's another variable. So C is like if you do P plus uh uh yeah, like I guess it's like P plus Q plus R. The leftmost digit of that is C. Um, so I guess what they're saying is like, so firstly for C, we can say like, so P plus Q is C1 S1, and then you add an R to that, you're gonna get C S. Um, so like C1 S1 plus R equals CS.
C1 S1 plus R equals um
Yeah, equals CS.
how do you
Or
get
C,
C2
yes.
again? C2 is that S 1 plus R.
The C2, well, C2 is the leftmost digit of S1 plus R.
Okay.
Yeah. And yeah, so and the S1 plus R is something that comes up like because like the first thing we did, we added P and Q and we got C1 S1. Then we need to add R to that to find like the sum of all three. And C1 S1 plus R, for the rightmost column of that, we've got to do S1 plus R, and so then we've got our second equation, S1 plus R equals C2S. And well, we have already that S then is going to be the rightmost digit of P plus Q plus R. But so maybe it could be helpful to also write like C1 S1 plus R equals CS.
C1 S1 plus R equals CS.
Yeah, and maybe write it like with the C1 S1 above the R.
Right.
So that the columns are visible.
Let me move this.
Yeah. So what we're doing here is like so we want to do this addition, and then the rightmost column we're doing S1 plus R, and we know that S1 plus R is equal to C2S, but we want to figure out like what if if that C2 is a 0, we don't need to worry, because like if that C2 is a 0, S1 plus R is just S, and then we just put in the C. The C1 is just gonna the C is just gonna be C1, but then we've got to worry if like S1 plus R is like 1 0. And then we've got to carry the 1 and do like 1 plus C1. So let's see what they say next. Like yeah, so the C, it'll be a 1 in the case that addition of P and Q gives a carry of 1. Like eventually we'd be doing S1 plus R and we carry 1 and do like 1 plus C1. Or it'll be C will be 1 in the case the addition of P and Q gives a carry of 1, or in the case that the addition of S1, the rightmost digit of P and Q, and R gives a carry of 1. In other words, C equals 1 if and only if C1 equals 1 or C2 equals 1. Interesting. So, oh, okay. So I guess I think I might be able to get it. So it was proven earlier that C1 and C2 aren't both 1,
Right.
and now we're going to use that fact. So first case, suppose that C1 is 1. Then we're gonna if C1 is 1, then we're going to be doing, oh yeah, well if C1 is 1, then we're going to have P plus Q equals 1 0, because the only way you can get a sum of binary digits have a 1 as its left digit, is if you have like 1 plus 1 equals 1 0. So if C1 equals 1, that means that P plus Q must have been equal to 1 0. So that's what the C1 S1 is going to be 1 0. So then we're just going to have like 1 0 plus R. 0 plus R is R, whatever the binary digit R is. And then we'll have, so 1 0 plus R, we'll have a 1 as our C, the leftmost digit. Yeah, did that?
Let's see. No pun intended.
Oh, yeah. Oh, that's a great pun. Yeah. So
So
you see why if C1 is 1, then C has got to be 1?
if C1 is 1, C has got to be 1 because C2 is going to be 0. And I'm missing a block here. So what's the big picture of how you construct C? It's like
Oh,
first you get C1 in S, then you add R to C1 and S, and adding R to S gets you C2 and S2. And then what do you do with the C1 once you have a C2 and S2?
yeah. Well, I think the idea is like the C is just whatever the leftmost digit of the whole sum ends up being.
Oh, you
Like
don't even add them or anything. It's just it's a exclusive or between the C's.
yeah, yeah. So they're like all, yeah, they're like different variables where like yeah, like first you add P and Q, and that's gonna give you some two-digit binary number C1, and we'll call the digits C1 and S1. And then so then whatever C1 S1 is, we're doing P plus Q plus R, so we got to add R to C1 S1, which was P plus Q. And so to do that addition, we first got to do the rightmost column. That's S1 plus R. And that's going to give us some binary number. Call it C2S. And then we'll just use C to represent whatever the leftmost digit of the whole sum ends up being in the end. Yeah, so, and we have that if C1 is 1, well, firstly, if C1 is 1, then C is going to be 1. And the reason for that is that uh like if C1 is 1, then P plus Q has to be equal to 1 something, because C1 S1, C1 is 1, so 1 S1. um the S1 has to be 0 because like if you're adding two binary digits and you get 1 something, the
Right,
only way
right.
for that to happen is 1 plus 1 equals 1 0. So now our C1 S1 is 1 0, and we're adding R to that. And well, 0 plus R, that's just going to be R. Uh, R is either 0 or 1. And then and then for our leftmost digit, we're just going to have the C1 coming down. And we know that that's 1. So in other words, like 1 0 plus R is going to be 1 R, where R is either 0 or 1. So the C, the leftmost digit, is 1.
Right.
Yeah. So that's why like C is 1 in the case where C1 is 1. But what about the case where C2 is 1? So in the case where C2 is 1, then we know that C1 is 0 because C1 and C2 can't both be 1. So we're going to have P plus Q equals 0 S1 in that case. So 0 S1, so we'll have 0 S1 plus R, and which will be either 0 1 or 0 0 plus R. And so we're assuming that S1 plus R is equal to 1 something. Uh, or actually, never mind. So another way of putting it, like, so C1 is, we know, is 0. So C1 S1 plus R is 0 S1 plus R. In other words, just S1 plus R. And our second equation, we know S1 plus R is C2 S2. And we're assuming C2 is 1. So S1 plus R is equal to 1, whatever S2 is. So the leftmost digit is the C2, which is 1. So we called the leftmost digit C, so C ends up being 1.
But we didn't agree that C2 has to be 1 if C1 is 0.
Oh yeah, well we did because we proved that C1 and C2 aren't both 1.
But we
So
didn't prove.
yeah, right. Yeah, so we got to do a third case, which is like there's another possibility like C1 and C2 could both be 0, and then we got to look at what happens there.
Yeah.
Yeah. And so they're saying that like that C equals 1 if and only if C1 or C2 is 1, which means that C1 should be 0 if C1 and C2 are both 0. So let's say that C1 and C2 are both 0, then well, P plus Q equals C1 S1, which is 0 S1. So so C1 S1 plus R is 0 S1 plus R, or just S1 plus R. And S1 plus R for our second equation, that's C2S, and we're assuming C2 is 0, so S1 plus R is just S. So our whole sum then is just going to be S sum, or we can write that as 0S since we're using 2 digits sum. So our C, the leftmost digit of the two, is going to be 0.
When they're both 0. Yeah.
Yeah, so we got that like when C1 or C2 is 1, C is 1, and when C2, 1 and C2 are both 0, C is 0. And then we got to come up with a logic circuit based on that.
Hmm.
So I guess maybe we can go down and like try to figure out how the logic circuit is working based on that.
How it's working. I'm surprised they don't want us to do it ourselves first. We'll
Yeah.
add.
Yeah, it'll be kind of hard to, I guess, I mean, like we can think about some aspects of it, but like, yeah, I guess the first step is easy. Like, we're doing P plus Q plus R. Well, P and Q, we can just put them through a half adder because they're binary digits. And the half adder is going to give us a carry and sum, because P plus Q is C1 S1, so it'll give us the carry C1 and the sum S1. And then our other input is R, so they have that on the left too. We want to add that to the sum of, we want to add that to C1 S1. And what we know is that I wonder where the T comes from, but
Right.
yeah, I think they're maybe not consistent with the variables. But well, I guess first we can do the digit by digit. Like so we know that when we do C1 S1 and then we add R, we want to get which should be CS sum. Uh and the CS, let's see. Yeah, the
If you
so if
add.
C1 and C, oh,
Right.
I think I see what, I think I see where the AND gate is coming from, because like C1 and so our leftmost digit is going to be 1 just in the case where, oh wait, uh, okay, so they're, so first they're, okay, so I think I see what they're doing. So first they added P and Q using a half adder, and they get the C1 and the S1, and then so now we want to do C1 S1 plus R. So for the rightmost column of that, we've got to do S1 plus R. So the S1 and the R go into another half adder.
Right. And you get C2 and S2, right?
Yeah, yeah. So they should have put S2 instead of T. I guess that was a mistake. Um, and then the S2, that's going to be the rightmost digit of our final sum. So that's going to be our first out, the bottom output there. And so now they have the C2 and the S1 going into an AND gate. I think they should have had it going into an OR gate though, because we want to have our leftmost digit be 1 just when C1 or C2 is 1, not when both of them are 1, because it's impossible for both of them to be 1. So I think they might have made a typo, and maybe they meant to put an OR gate at the end there.
Hmm.
Yeah, because like the what they're writing as the S there, that's what they called C originally. It's the leftmost digit of our final sum, and they showed that the leftmost digit of the sum is going to be 1 precisely when either C1 or C2 is 1. So I think we should have an OR gate there.
So let me observe. Yeah, I guess it would be an OR gate, not an AND gate. And that actually is the shape of an OR gate. Typically,
Yeah.
so maybe that's what's meant. This is like one of the worst chapters to be confused, to be like riddled with typos.
Yeah. Yeah. Yeah, maybe the author got confused.
Hilarious.
Yeah, with all the different like variables floating around. Yeah.
Well, let's see if their truth table is consistent with what we understand here. So P, Q, and R all being 1. I know that would be like saying 1 plus 1 plus 1. So that would, the P and the Q would get you 2 or 1, 0. And then if you add 1 to that, you would get 3, 1, 1. So this would be your C and your final S. So that's
Yeah.
what we got.
Yeah.
With P, Q, and then R being 0, you would first get your C1 and your S1. Your C1 would be 1 and your S1 would be 0. Then you add R to that. And your final C would be the or the I guess the XOR of your C1, which was 1, and C2, which was 0, because when you summed S1 and R, C2 would turn out to be 0. I guess you don't even have to sum S1 and R anymore, because we have logic that proves that C2 can't be 1 if C1 was already determined to be 1.
Yeah.
I want to look at that one more time. So C2 can't be 1 because you can never have a situation where S is 1 and R is 1. R can always be 1. So you can never have a situation where S is 1 and C1 is 1. So PQR in an addition situation, P plus Q can never equal 1, 1. I guess that makes sense because P and Q are limited. They can only be at most 2, whereas 1, 1
Yeah.
would be 3.
Yeah. Yeah, exactly.
Okay. So, and then what we determined is C2, right? So you can never have this situation because, which means you can never have the situation where R is 1, which would produce a C2 that is 1 and a C1 that is 1. I guess that's just like I guess that's just like obvious logic, but when you're learning it for the first time, this is how you would have to learn it. You have to just be told this.
Yeah. Yeah, exactly.
Oh, okay.
Yeah. And I guess maybe we can do there's like one last thing that relates to this topic. Then before we do, and then next time we can do the next topic that it discusses. It just kind of looks at how you can combine how you can do 3-digit binary numbers.
Three digits.
Yeah, yeah. I guess it has a diagram like combining the different adders.
So, half adder, full adder, and a full adder. See if it makes sense. The half adder. Okay, so you're adding two one-digit numbers, and you get a C1, and you get an S1. I guess which they're calling Z. Oh wait, there's some words here. Two full adders and one half adder can be used together to build a circuit that will add to 3-digit binary numbers.
Yeah, and then they just call the sum WXYZ. Um, so yeah, I guess the idea is like, well, you do PQR plus STU. So the rightmost column is going to be R plus U. So you put the R and the U into a half adder, and then you get the sum C1 S1. The S1 is going to be the rightmost digit of the whole sum. And then you do what you did before. You put the C, I guess let's see. Um, oh, um, oh, so you then need to add you need to add this. We add in the second column. You're adding the Q and the T, and you're also adding the C1 because mm, I guess because if the C1 is a 1, then you gotta carry a 1 maybe, or um
Let's
I
see.
don't know. I don't know. I wonder why you're adding the C1 to the Q and the T. Maybe, oh yeah,
Q.
it'll be easier. Oh yeah, it's good to write it down. Yeah, the
So
mm,
maybe it's expecting us to do it like intuitively first and just understand how adding works, and then after we understand how it would work naturally, this is how you would implement that understanding. I assume, because it doesn't really explain. So let's see. The half adder part, we understand that already. Then the full adder part wasn't, so the definition of a full adder, let's look at that again, is okay, the half adder and another half adder with that,
yeah,
with the or between the C's. Um,
yeah. And I guess what a half full adder does is it adds 3 digits and then gives you the 2 digits of the result.
right. You said that's what
So we can just kind
that's
of
what a full adder does.
yeah. So we can think in terms of like what it does, and then we're plugging Q, T, and C1 into a full adder, meaning we're adding them and getting the digits of the
Oh,
result.
so you're putting C1 and Q and T. So Q and T. So first, C1 was composed of R and U.
Yeah, it was the leftmost digit of the sum of R and U.
And I guess we just
Um,
threw away the S, or we call it Z. Maybe it's going to be used later. It's not.
yeah, the Z is that one's not used later because like so R plus U equals C1 S1 or
Ah,
it equals C1 Z. The Z is going to be the rightmost digit of the whole sum. Oh yeah, and then the so like suppose that so Z could so C1 Z could be one of three things. It could be 0 0. in which case adding C1 to Q and T would just be 0 plus Q and T. It could be C1Z could be 0, 1, in which case the C1 is again just 0, so it doesn't contribute. And then the one other possibility is that C1Z could be 1, 0, in which case you'd have to carry a 1, and then you would be doing 1 plus Q plus T. In other words, C1 plus Q plus T. So you would in fact be doing C1 plus Q plus T when you're doing the addition.
So the Z is no longer needed, I guess, because, well, how would you tell the difference between 101 plus 111? Wait, no. How would you tell the difference between two additions which both have the one equaling 0?
Yeah, well, if you have C1 equaling 0, what that means is that R plus U equals either 0 or 1. So there's no extra 1 digit on the left of it. So if you have C1 is 0, R plus U equals 1 or 0, so the Z is 1 or 0. And
Mm-hmm.
then you just keep on going and do Q plus T. Uh,
Oh,
yeah,
Z,
and then,
yeah, isn't thrown away. It's a part of the answer here.
yeah, that one's part of the answer. So like, yeah, so R plus U, it equals some 2-digit binary number C1Z. The Z part, that's going to be the rightmost digit of the whole sum. And then the C1 part, if it's 0, then we just move on to doing Q plus T. If it's 1, then we carry the 1 and we do 1 plus Q plus T. So either way, we're doing C1 plus Q plus T in the next column, because if C1 is 0, then we have 0 plus Q plus T, which is just Q plus T.
How does the full adder deal with C1 being 0 again?
Uh, I guess that nothing special would need to happen with it being 0. The full adder just adds C1, Q, and T. So it's just gonna, whatever C1 is, you're just gonna add the 3 of those, C1, Q, and T, and it'll give you the 2 digits of the result.
Oh, okay. And how does it add them?
Oh well, it adds them like in the complicated way that we saw in the previous part. Like that's how it adds them. Yeah, so it's kind of like treating it as a black box now. Like it's um now that we know the mechanism of how it works, then we can just write full adder and say like that's the internal workings of it.
Right? I just like
Yeah.
forget how it works so easily. I feel an urge to remember over and over again how exactly does it work. Um, so okay, I know it adds 3 numbers, and it does that by adding the first 2 numbers to get your C1 and S1, then adding R to S1 to get C2 and S2, and then the XOR gate on the C1 and the C2 to get the final C. And the final S is whatever S2 is, right?
Uh
Let's
yeah,
make
the
sure.
or well, I guess these may mislabeled everything. I think like on the right, the S it really was labeled C originally, and then the T was really labeled S originally. So it should be CS instead of ST.
Right.
Yeah, so that's an unfortunate mistake.
So S2 is the final S.
Yeah.
Okay. So whenever C1 happened to be 0, because you added P and Q and C1 was 0, um,
Yeah, then you have 0 plus Q plus T going into the full adder.
right. So there's that XOR of C1 and C2. So yeah, it would just take whatever this C of R plus S1 as its final C.
Yeah. Yeah.
Okay, which was Q and wait, which was
Yeah, because
Q
like
and
in
T,
the
right?
yeah, because now we're doing PQR plus STU. So the second column we have Q plus T. And then we'll be doing like plus C1. Because like we start out with the rightmost column R plus U, and R plus U is going to equal something with two binary digits. We'll just call those C1 and Z. So R plus U equals C1Z. If C1 is, and then so the Z ends up being the rightmost digit of the whole sum. If the C1 is 0, then we can just keep going and do Q plus T, go to the second column, and Q plus T equals 0 plus Q plus T, so it equals C1 plus Q plus T. Um, if the if R plus U is so R plus U is C1Z. If the C1 is 1, well, we can't have two digits in one spot. So we've got to carry the 1. So meaning that we put the 1 above the Q and the T. So then we'll do 1 plus Q plus T, which is C1 plus Q plus T. So in other words, like in the second column, we're going to be doing C1 plus Q plus T. So we put all of those into a full adder to figure out what the sum would be.
One thing is like, why is Z the final answer, whereas in the full adder, S1 was not the final answer. It's not the final S. The final S was
Uh,
S1 plus R, which I guess in this case would be like
yeah.
um I don't know if there isn't really is there an R here?
Uh, well, there is an R, but like they're using the variables differently in this case than they
Right.
used them before. Yeah.
Because we have the S1, but where's the plus R?
Yeah, there isn't one. They kind of just like, yeah, I guess they kind of just want us to forget about how the variables were used before and just like start over. And so like so we don't have like they're not used the same way anymore. So
Right.
S1, like it's kind of like R and U represent digits of the originals, or of the things that we're adding, the rightmost digits of each. And then S1, uh that's just the leftmost digit of the sum of R and U, or sorry, the rightmost digit. So it's
Right.
like yeah, R plus U equals C1 S1, and then we'll just call S1 Z, um, because S1 is going to be the rightmost digit of the whole sum.
Yeah, it looks like there's some minor mysterious like mathematical differences between adding three-digit numbers and the full adder. Because in this case, we're just assuming S1, we're just allowing S1 to be the final S immediately without adding R, which in this case, I guess would be like Q or something. There is no R, you know,
Yeah,
in the sense that it's not exactly like the full adder example.
yeah,
It's not exactly the same
yeah,
pattern to create the answer with three-digit numbers.
yeah, yeah. Yeah, I guess maybe it has to do with like partly with the fact that we already have the mechanism of the full adder, and like we don't need to like worry about the details of it anymore. But yeah, I guess they can kind of just do like we're doing PQR plus STU. Then we add go by going column by column, starting with the rightmost one. So the rightmost column R plus U. We'll just call the result of that S1 C1. Or sorry, C1 S1. Um, S1, whatever that is, that's going to be the rightmost digit of the whole answer, which is Z, because we're assuming the whole answer is WXYZ.
Right. Okay, well,
Yeah,
let's move on down the tree here. So S1 is our Z. Then we have
yeah,
C1, put it into the full adder with Q and T.
yeah. And that gives us S2 C2. So, or sorry, no, C2 S2.
Right.
So yeah, and that's the same thing again. Like, well, the S2, that's our next digit. That's the Y. the digit
So
that goes in that column.
it did it
The
again, right? It just made it the digit that goes in that column without any like extra comparison. So
yeah,
okay,
yeah,
I like it. It's easier. So when doing it this way, you um well, I see half adder, full adder, which makes me think maybe this is just how it works for. I wonder how it would look for a 4-digit um,
yeah. I think you would go
addition.
kind of do the same thing like another time. I guess
That's what
you
I'm
would.
guessing. Just never know.
Yeah, yeah. Let's see. You do well. So we did the full adder with C1, Q, and T, and then we got C2, S2. S2 is our next digit of the full answer. The
Uh,
C2, if it's 0, we don't need to worry about it. If it's a 1, then we carry a 1. So we're going to have C2 plus P plus S, because if C2 is a 1, we're carrying it. So we're doing 1 plus P plus S. If C2 is a 0, we're just doing P plus S, which equals 0 plus P plus S, which is C2 plus P plus S. So so we do that, and then we end up with um, C3 S3, and then that's going to be the rightmost digits, C3
wait,
S3.
repeat
If
that
we
one more time about like you just I think you just outlined what a full adder does. C2.
Yeah,
So yeah, C2P and S.
yeah, it adds them, and then it gives you a sum, which is C3 S3. That's just what they call it. Um, C3 S3. We've got the sum, so those will be our rightmost digits. But if we were adding a 4-digit number, then we'd need to maybe carry the C3. So then we'd plug C3 in, and then we'd add like the leftmost digits of the numbers we're adding together with C3 into another full adder. So we just do the same thing again.
Well, most likely, yeah. My question is like, so what is this S3 composed of? Like I
Oh yeah,
know that S2 is S1 plus R, right?
yeah. Well, I guess maybe not anymore. I guess it's kind of like that's what S2 was when we were kind of looking at the mechanism of the full adder.
Right.
But now it's just kind of like we're taking C1 plus Q plus T. We're just going to call the sum of that C2 S2. So S2 is just whatever the rightmost digit of that sum is.
Uh,
Yeah, so it's kind of like we're kind of like setting aside how the variables were used before.
oh,
Yeah,
okay.
yeah. And then similarly, we do C2 plus P plus S, and we just call the sum of that C3 S3.
Interesting. It's interesting that we can do that. I feel like that implies something like like was the full adder we learned before just one of many implementations or something? Like as
Well,
long as the full adder gives you the right 2-digit number, do we not need to know how it works?
yeah, yeah. It's kind of like we already know how it works, and then now like the way they put it earlier was like we treat it as a black box, meaning like we kind of just like treat it as something that we plug inputs into and get outputs out of, and
Ah,
we don't worry about the internal mechanism. So like it's kind of yeah, it's kind of like how like if you prove a theorem, then you can just use it without having to prove it again every time. Similarly, like now that we
ah,
know how full adder works, we can just like put a box that says full adder and know that it adds 3 things, and then we don't need to worry about how it works.
right. I mean, that's interesting, interesting, interesting.
Yeah.
The what makes it so interesting to me is that it really looks like it's different and yet the same. Looking at it zoomed in, like whenever we're going through it step by step, it almost looks like it. What I hope is the case is that in this third example, they're giving us a bird's eye view, and it's just so shockingly simple from a bird's eye view. that's what I hope the case is. Like the experience of this is like what we learned is like slightly different than this bird's eye view version
Yeah,
in like little important ways, like, but having this bird's eye view does help me um see the forest rather than being lost in the trees.
yeah, yeah, yeah. That's really cool.
Yeah,
Yeah, and then I guess next time we can do two's compliments. That'll be
indeed.
interesting. Yeah, yeah. So I like this lesson. I guess definitely some good brain exercise. Because yeah, it started out not too hard, but then I don't know. At least for me, this was the hardest part so far.
Right. I guess that was the most convoluted part.
Yeah,
Yeah, that was definitely the most convoluted content. But it was actually like fun getting through that. I have memories of getting like discouraged or lost or like falling off of the wagon in convoluted expositions of how things work.
yeah,
It's it's nice like actually buckling down and unraveling that convolution.
yeah,
Such a satisfying victory.
yeah, yeah. It's fun.
Yeah,
Yeah, it's a good exercise, kind of like solving a puzzle.
indeed. Huh. It does, it just takes focus, I suppose. Takes this extended focus. Losing focus is really the probably the crux of the reason why a convoluted exposition can be discouraging.
Yeah, I definitely. Yeah, and I imagine like what if this was being taught in a
Oh
class and
yeah.
like it's like in a lecture, then like yeah, imagine if I was listening to a lecture, I wouldn't understand anything because it would go too fast. Like you need a lot of time to really think about
Mm-hmm.
and understand all the parts. Like yeah, so it's good to be able to do that. Yeah, because like if this were in a class, I guess I would probably just be like looking at it for a couple hours after class to try to understand it. I wouldn't understand it during the lecture.
Exactly.
Yeah.
So, hmm,
Yeah.
I guess I'll start like I don't know, ending stream. We don't necessarily have to stream Hearthstone matches and like until there's a gang of people.
Yeah. 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 Makes sense.
Hmm. Did you still want to play, or did you really just want to stream it?
Uh, either way is good. I mean, yeah, I'd enjoy playing it either way. Yeah, if you're up for it. Like if you don't need to go to bed or anything, because I'm not going to bed for like a some time.
Oh, nice. Yeah, I'll play at a nice what do you call it? 2 out of 3 game.
Yeah, sounds good.